The environment is evolving every second. Economical and technological diffusion have become more advanced, and consumer demands are rising. Due to these factors, pollution is increasing day by day. Food waste is a dominant contributor to pollution. Specifically, 23 million tons of coffee are left as residue per year, which contributes to soil pollution and global warming. In addition, the mass usage of commercial fertilizers is a major producer of greenhouse gases and leads to the eutrophication of waterways. We are Charlene, Layla, and Cecilia, and our solution to the problem of food waste pollutants is to transform them into an effective, natural, and practical alternative to commercial fertilizers in order to ensure the longevity of the environment, maintain plant and animal biodiversity, and promote sustainable development. Inspired by agar, coffee residue, and eggshells, the three initial letters created the ACE fertilizer. First and foremost, agar is a natural marine biopolymer that has a double helical molecular structure that is capable of holding water molecules in its interstices. This forms a thermoreversible gel-like substance in 1% agar solution, making agar the superior binding agent. Moreover, agar's diffusive property makes it a slow-release fertilizer that is also biodegradable through microbial action, eliminating the risks of fertilizer burn and soil pollution, which is commonly seen in commercial fertilizers.
Coffee residue contains nitrogen, which allows plants to absorb and convert light energy into chemical energy through photosynthesis, promoting healthy plant growth. Coffee residue contains a caffeine compound that distorts insect behavior by inhibiting phosphodiesterase enzyme production, which causes an increase in intracellular AMP, a messenger in the insect's brain, which decreases their ability to consume food and to reproduce, preventing soil-borne diseases as a result. Infrared spectroscopy shows that coffee residue is acidic, so alkaline eggshells are added to adjust the acidity of ACE. Eggshells are made up of 95% calcium carbonate, which assists in the growth of plant structural components, decreasing the chances of necrosis. In part 1 of our investigation, ACE is synthesized by boiling agar, eggshells, and coffee residue in this ratio. After boiling agar with water for 10 minutes, we added the corresponding amount of coffee residue and eggshells powder required into the mixture, which is then transferred into identical plastic molds which ensure equal distribution of 3 components. This solidifies to form the ACE fertilizer. It is then added to the soil of 500 different trials of green beans where their growth and health are regularly observed and monitored over a period of 2 months.
We then tested the effectiveness of ACE in Part 2 using parameters of growth rate, leaf greenness, biodegradability, soil pH, and dry mass. The growth rate results shows that beans in ACE grew 120% faster than those without fertilizer, and had similar growth to beans in commercial fertilizers, proving as an effective alternative. T-tests showed that beans in ACE grew significantly taller than beans in no fertilizer, with a p-value far less than 0.001. T-tests between beans in ACE and 2 of the 3 components shows that ACE plants also grew significantly taller, proving that each of the components itself is a large contributor to such promotion of growth, and hence ACE is the optimal combination of fertilizer for plant growth. The greenest color test compares leaf color with 4 different shades of green. Results shows that all beans have the darkest shade of green, indicating that ACE promotes an optimal chlorophyll content. The biodegradability results demonstrates that ACE degrades in soil within 10 days, showing that it is eco-friendly as it can be reabsorbed by the environment. The pH soil test shows that the pH value of pure soil, soil with ACE, and soil with commercial fertilizers are all 6, which lies in the optimal range of general soil within 5.5 to 7. Thus, ACE does not alter the pH level of soil, ensuring that it does not pose any toxic effects to plants. The dry mass test shows that ACE plants have the most dry mass with 1.2 grams. This shows that ACE plants can accumulate the most organic material, including cellulose, protein, and starch. Ultimately, ACE's slow release feature promotes stable growth. It is an effective, eco-friendly solution for mitigating the food waste problem. To further extend our investigation, we are currently experimenting with a variety of plants including basil and black-eyed pea and changing the proportion of coffee residue in eggshells to ensure ACE's universal applicability. Thank you.